whenever we give an outside talk. So thank you for inviting me to present my ideas and results in this e-seminar. Once again, thanks Rajesh. It's a pleasure to be here. So my talk is concerned with an introduction to Fan-Theobald-von Neumann systems. So these are big names. I've been working on this for a while. The presentation today is based on 3 articles. The first one is posted in archives. It is about optimizing certain combinations of linear distance functions over spectral sets. I'm partly optimizer, partly a matrix theorist, partly functional analyst. I used to work in several complex variables long time ago, but I don't do that anymore. Mainly because of some people in Wisconsin, particularly Mangasarian, Robinson and others, have moved over to optimization. So that reflects my interest in this area. The second article, Commutation Principles or Optimization Problems on Spectral Sets in Euclidean Jordan Algebras, will appear shortly in optimization letters. The third article is being written. It should be finished shortly. I'll post this in archives. Most of the references that I'm going to mention in my talk appear in this third paper, but they also appear in the other 2. Okay, so let me start with the definition of a Fan-Theobald-von Neumann system, and I'll start with some examples and describe some properties and all that. So the definition is very simple. We look at a triple VW lambda, where V and W are real inner product spaces, and lambda is a map that goes from V to W, and this map can be nonlinear. Now, for any U in V, we write bracket U for the set of all x in V with lambda x equals lambda of U. So you can think of this as some sort of an orbit generated by U. I know that this is a language used in dynamical systems, but this orbit is different. I'll give you examples of this shortly, but let's go through the definition. So for any U, bracket U denote the so-called lambda orbit of U. Then one says that the triple VW lambda is a Fan-Theobald-von Neumann system if the following 3 conditions hold. Lambda is norm-preserving. So it simply means that the norm of lambda x computed in W is the same as norm of x computed in V. And this should be true for all x in V. So lambda is norm-preserving. For every x, y in V, the inner product between x and y is less than or equal to the inner product between the corresponding lambda x and lambda y. Notice that the first inner product is computed in V, the second inner product is computed in W. And the third condition is the key condition. It talks about a linear function having a maximum on a lambda orbit. So the maximum of the linear function c dot x over the lambda orbit of U is given by the inner product of lambda c and lambda u. Notice that this should be true for all c and all u in V. Now, if you look at the maximum, the objective function here is c dot x. That is always less than or equal to lambda c dot lambda u. And because x is in the orbit of U, lambda x equals lambda u. So you could infer from this maximum that c dot x is always less than or equal to lambda c dot lambda x. And if I replace c by x and x by y, then it gives you the second item in the definition. So in other words, the second item is a consequence of the third item. And if I put x equals y in the second item, you get norm x less than or equal to norm lambda x. So one can condense these three items to only two. But for clarification purposes, I have stated all the three conditions. So once again, this triple V W lambda is a Fan-Theobald-von Neumann system. I'm going to abbreviate that as FTVN system if the three conditions hold. That's it. Now, I mean, my experience is I've seen lots and lots of papers where one comes up with 10 conditions and what they prove one tiny result. But that should not be. I mean, that's not the right way to go about doing research. So you need to have minimal number of conditions with the maximum number of results and concepts. And that is my goal here. I have three conditions here. Maybe they are all related. But as you will see, you will have lots and lots of results coming out of these three. Okay. Please stop me at any stage and ask questions. Inequality that appears in the second item will be called Fan-Theobald-von Neumann inequality. I'll tell you why I'm using these three names for this inequality. These names will appear in various examples. And the equality x dot y equals lambda x dot lambda y. And this happens sometimes. So whenever this equality holds, we say that x and y commute. This is a new concept that will appear throughout my talk and throughout this particular analysis. So there is a new concept of commutativity in this theory. And this concept is new even for matrices. So number of questions arise. Why are we using the big names? What are some examples? Are the examples relevant? Are the examples useful? What concepts and results can be obtained in this general setting? What are some applications? What are some open problems? I mean, without open problems, the theory is almost dead. So you need to come up with the new problems to solve. We are going to address some of these in the course of our talk. And a lot more will not be covered, as you will see. Now, just to summarize, examples include spaces of real / complex Hermitian matrices, Euclidean Jordan algebras. These will include even quaternion Hermitian matrices, octonion Hermitian matrices, and the so-called spin algebra. Also, spaces induced by certain hyperbolic polynomials, normal decomposition systems, Eaton triples, etc., etc. The new concepts deal with commutativity, majorization, doubly stochastic maps, and all that. And of course, I'll mention applications that deal with optimality conditions, complementarity problems, variation and inequality problems, and so on. Okay. So I'm going to start with two elementary examples and then move on to some rigorous, serious examples. The first example is a simple one, that V be a real inner product space and lambda going from V to R is simply the norm. So lambda x equals norm of x. So lambda goes from V to R. Immediately we observe that lambda is not preserving from V to R because the absolute value of lambda x is the same as norm x. So lambda is non-linear and non-preserving. And we have the Cauchy-Schwarz inequality. So x dot y is less than or equal to norm x times norm y. But our norm x is nothing but lambda x and norm y is nothing but lambda y. And the inner product is taken in R. So it is simply lambda x dot lambda y. So in other words, our condition 2 of the FTVN system holds in this particular case. And notice that when we are using this inner product space, if I maximize the linear function c dot x over the unit sphere, by duality, I simply get the norm of C. But I can scale this thing. This maximum simply gives us the following: maximum C dot x such that norm x equals norm u for a fixed u is nothing but norm C times norm u. And replacing all the norms by the corresponding lambdas, this will translate to maximum C dot x such that x in the lambda orbit of u is nothing but lambda C dot lambda u. And notice that this is the third item in our definition of FTVN system. So we have norm-preserving property. We have this lambda increasing in the inner product. That is the second bullet. And the third bullet says that the maximum is attained at this lambda C dot lambda u. So in other words, this triple V or lambda is a FTVN system. Now here, x and y commute if and only if one of them is a non-negative multiple of the other one. This is simply a consequence of the equality situation in the Cauchy-Schwarz inequality. So this is our first example. Here is the second one, simple one. Take V to be a real inner product space. Let S from V to V be a linear isometry. And we know that a linear isometry preserves the inner product. Then with lambda x equals S of x. So this lambda goes from V to V. This triple V comma lambda becomes an FTVN system. And because S is linear isometry, lambda preserves the norm, and the inner product of x dot y is the same as Sx dot Sy. So the second item in the definition is obviously true. And moreover, in this situation, the lambda orbit bracket u, which is x at that lambda x equals lambda u, which translates to Sx equals Su, reduces to just the singleton set u, because S is a one-to-one function. So this triple is an FTVN system, and because x dot y equals Sx dot Sy, that is lambda x dot lambda y, any two elements in this space in the system commute. So this is like a discrete system. That is the way that I can think of this.
Professor
Now
Gowda,
we move on to some. Yes.
What is the multiplication you are considering here in that inner product space?
Hold on 1 second. Now remember, V carries the same inner product in both the spaces.
Okay.
So lambda x is actually linear in this case.
Yes.
So V carries the inner product. We use the same inner product in both the settings. So x dot y is computed in V, Sx dot Sy is computed in V, and they're equal because S is inner product preserving. Is that okay?
The commuting you means in terms of inner products.
No, okay. Let's go back to this one.
Okay.
I said I'm going to make that precise later on.
Okay.
See, the equality x dot y equals lambda x lambda y, whenever it holds, defines the commutativity of x and y in this system.
Okay.
So generally you have x dot y less than or equal to lambda x dot lambda y. This is the so-called FTVN inequality. Whenever you have equality, that defines the commutativity of x and y in this system. So that is how I define commutativity. I say that x and y commute if the inner product of x and y equals the inner product of lambda x and lambda y. So you have the Fan-Theobald-von Neumann inequality. Whenever you have equality there, you say that x and y commute. That is my definition of commutativity.
Okay. Thank you.
Okay, I mean, this is a new concept. I mean, it's strange that commutativity comes in this particular form, as you will see that this is new even in the case of matrices.
Okay.
So we have covered these two elementary examples. I'll move on to a non-trivial one. So this is our Euclidean space Rn. And in Rn, I'm going to regard objects as either column vectors or row vectors depending on this situation. Because for typing, I can think of them as row vectors. When I'm dealing with matrices, matrix multiplication, I think of them as column vectors. Okay. I take two vectors x and y with components x1, x2, xn, y1, y2, yn. I define the so-called x circle y, which is simply the vector consisting of the corresponding component product. That is, x circle y is x1, y1, comma x2, y2, dot, 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 x and yn. Now, if you think of the vectors as matrices, diagonal matrices, this is nothing but the so-called Hadamard or Schur product. But in this setting, I want to think of this product as the Jordan product because this gives us an example of an Euclidean Jordan algebra. And normally one will not see this type of a product in ordinary matrix theory, but it becomes important in this particular situation. All right. So what is this x circle y? It is simply the component-wise product. I will call that the Jordan product. And notice that if I take x equals y in here, the set of all x circle x as x varies over Rn is nothing but the non-negative order. So this gives us a clue. So if you're in some sort of a Jordan algebra setting where x circle y is defined, when you take x circle x, this is the so-called set of squares that induces a closed convex cone, and we'll see that that defines the so-called semi-definite cone or a symmetric cone in various general settings. Okay. Coming back to Rn, for x in Rn, I will write x down arrow for the decreasing rearrangement of the entries of x. This is a standard notation. For example, in R3, if I take x equals -1, 2, 0, then x down arrow is 2, 0, -1. So you simply rearrange the entries in the decreasing order. If vectors x in Rn are viewed as column vectors, then x down arrow is p of x, where p is some permutation matrix p. So you start with x, you rearrange the entries of x, and what you get is this decreasing rearrangement. Now, way back in 1938, Hardy, Littlewood, Polya proved that in Rn, the inner product of x dot y, remember everything is usual inner product, x dot y is less than or equal to the inner product of x down arrow and y down arrow. And they also showed that the equality holds if and only if there is a permutation matrix P with P of x equals x down arrow and P of y equals y down arrow. In other words, equality holds if and only if x and y can be simultaneously transformed to their decreasing rearrangements. This is very useful. And now you are already beginning to see that if I take lambda x equals x down arrow, lambda y equals y down arrow, you get one of the conditions that I listed in my FTVN system. Now this immediately shows that for all CU in Rn, the maximum of the inner product C dot x such that x down arrow equals u down arrow is nothing but the inner product of C down arrow and u down arrow. And there is a simple proof. I'm not going to elaborate on that one. So, you can compute the maximum on the left and show that it is equal to the value on the right. Now, let us write lambda x equals x down arrow. We may think of entries of x as eigenvalues of the diagonal matrix with x as its diagonal. Then lambda x is simply the vector of eigenvalues of x written in the decreasing order. We call lambda the eigenvalue map because its in some sense deals with the eigenvalues of this particular vector x or the corresponding diagonal matrix. So this lambda is the eigenvalue band. Let us look at the lambda orbit of any u. What is it? It is bracket u equals x in Rn such that lambda x equals lambda u, but lambda x is x down arrow, lambda u is u down arrow. But we know that x down arrow and u down arrow can be written in terms of permutation matrices. So this lambda orbit is nothing but P of u, where P varies over the set of all n by n permutation matrices. So in this setting, lambda orbit of a vector u is simply the set of all hits from this permutation group. Now what is interesting here is this permutation group sigma sub n is precisely the set of all real invertible matrices A which preserve the Jordan product that I mentioned earlier. So whatever it is, if you put this circle product, Jordan product on Rn and view that as an algebra, then the sigma n becomes its automorphism group. That is one way of looking at the permutation group as an automorphism group. And this becomes important when we move to matrices and Euclidean Jordan algebras. Now, the result of Hardy-Littlewood polia that I mentioned earlier can now be rewritten in terms of our lambdas and lambda orbits. What is it? It simply says that for Cu in Rn, the maximum of the inner product C dot x as x varies over this lambda orbit of u is nothing but lambda C dot lambda u. Notice that everything is taken in Rn. But we know that lambda x is nothing but x down arrow. And in particular, the 2 norm of x is the same as the 2 norm of x down arrow. So this lambda is non-preserving. So if I put all the things together, I see that this triple Rn lambda is a FTVN system. Now in this system, vectors x and y commute if and only if a single permutation matrix takes x to x down arrow and y to y down arrow. Now what is interesting is, this is not the same as two things commuting in the ordinary sense. For example, if I look at R2 lambda, in this FTVN system, the vectors 0, 1 and negative 1, 0 commute, because if I look at the inner product of these two, I get 0. If I rearrange them in the decreasing order, 0, 1 becomes 1, 0, negative 1, 0 becomes 0, negative 1. Their inner product will also be 0. So the two inner products are the same. So in other words, these two vectors commute. However, 1, 0 and 0, 1 do not commute in this FTVN system. This becomes important later on when we talk about commutation principles and all that. Okay, 1, 0 is orthogonal to 0, 1. They are non-negative, they are complementary, but they do not commute in our system. Now, when you view vectors as diagonal matrices, any two vectors commute. Now we shall see that the usual matrix commutativity is weaker than the commutativity in a corresponding FTVN system. Now that we are still working in Rn, I can talk about majorization. Now all these things can be found in Bhatia's book on matrix analysis. This is not new. This is all classical. Let us recall majorization in Rn. Given vectors u and v in Rn, we say that u is majorized by v, and write u. I mean, you have that notation u major, that symbol v. If for all natural numbers k, 1 less than or equal to k less than or equal to n, the first k entries in u down arrow is less than or equal to the first k entries in V down arrow. This should be true for all k, and we demand that equality holds when k equals n. The sums are equal. Then a classical result of Hardy-Littlewood-Polya says that U is measured by what? V, if and only if U equals dV, where D is a n by n doubly stochastic matrix. Now, what is a doubly stochastic matrix? It is simply a non-negative matrix where each row and each column sum is 1. This is classical, nothing new here. This is the result of Hardy-Littlewood-Polya. Additionally, a result of Birkhoff says that every doubly stochastic matrix D is a convex combination of permutation matrices. This is also classical. I mean, you can find all these things in Bhattia's book. So, in this setting of Rn, U is measured by V if and only if U is in the convex hull of the lambda orbit of V. And here, this con refers to the convex hull. It is in this form we are going to extend the concept of majorization in FTVN systems. So U is measured by V if and only if U belongs to the convex hull of the corresponding lambda orbit of V. Now, a well-known fact, real n by n matrix D is doubly stochastic if and only if dx is measured by x for all x. And we are going to introduce the concept of a doubly stochastic map in our FTVN system by demanding that dx be measured by x for all x in that particular system. So that is how the generalization carries over. Before I move on to other examples, I want to, at this stage, give a polynomial interpretation for this discussion. This is where we get into hyperbolic kind of polynomials and all that. On the real vector space Rn, consider the polynomial p of x, which is the product of all the entries of the vector x. So p of x is nothing but x1, x2, dot, 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 xn. Then p is a real homogeneous polynomial. Now, homogeneous simply means if you replace t, x by t times x, where t is a number, then that t can be pulled outside of p. It simply becomes a power of t. So p of tx in this particular case is t raised to n times p of x. So p is a real homogeneous polynomial. Now let us take this vector e consisting of all ones. Then for any fixed x in Rn, look at the roots of the univariate polynomial. So what is this polynomial? Remember, I'm fixing my x. My polynomial, univariate polynomial is t, a real number, going to p of t e minus n. But p of x is simply the product of the entries of x. So p of t of e minus x is nothing but t minus x1 times t minus x2 dot 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 t minus xn. So what are the roots of this polynomial? Well, t equals x1, t equals x2 dot dot dot. So the roots are x1, x2, xn, which are all real. This is the key. So I start with a real homogeneous polynomial. I choose a vector e and I look at this univariate polynomial, little t going to this p of t of e minus x. Look at the roots of that. I require all the roots to be real. In this particular case, the roots are all x1, x2, xn. Then what do we do? With these numbers, with these roots, we can create a vector lambda x with decreasing components. So I take this x1, x2, xn. That is what I got in this setting. I create this vector lambda x with decreasing components. This is precisely our x down arrow. Well, notice that lambda x in this particular case, which is x down arrow, implies x equals 0. This is defined as the completeness of our polynomial p. I'm going to say that later. This lambda induces an inner product on Rn. Notice that this is all generated by the polynomial p. So start with the polynomial p, start with the specific e, generate this lambda x and use this lambda to define this inner product. Now, how do I know that this defines an inner product? That's a beautiful thing. This is covered in a paper of Bausch K et al. Written in 2001. I will mention that reference later on. So you define the inner product x dot y this particular way. Then immediately one can verify that x dot y is less than or equal to lambda x dot lambda y. But in this particular example, this x dot y is nothing but our usual inner product. And lambda x is nothing but x down arrow and lambda y is y down arrow. So you're recovering this classical result of Hardy Littlewood Polya out of this particular polynomial. This polynomial P, along with E given above, is an example of a hyperbolic polynomial. I'll say more about this hyperbolicity later on. Okay, so we have covered Rn. Now I'm going to move on to the spaces of Hermitian matrices. Let Sn denote the space of all n by n real symmetric matrices, Hn denote the space of all n by n complex Hermitian matrices, and let V denote one of these. Now here on V, I can define two things. The inner product is the standard one. X dot y is the trace of the product xy. Notice that the trace is always real, it can be shown. And x circle y is xy plus yx divided by 2. And one does not see this product in a standard matrix theory course. Now, why are we defining this product x circle y in terms of xy plus yx divided by 2? This is because even if x and y are, let's say, real symmetric or Hermitian complex, xy may not be real symmetric or Hermitian at all. So in order to get back something that is real symmetric or Hermitian complex, we add the two, xy plus yx divided by 2, and that will put us back in the same space. So x circle y is back in Sn or Hn, depending on the setting. And if I take x equals y in this product, I'll call this x circle y product Jordan product. If I take x equals y, I simply get x circle x. And notice that x circle x is nothing but x square. So if I take any matrix x, Hermitian, complex, real symmetric, whatever, x square is a positive semi-definite matrix. So this V plus that I have given here is the set of all positive semi-definite matrices. So what you get is the semi-definite cone. Okay. Now each x in V, remember V is either Sn or Hn, each x in V has a spectral decomposition. X equals U D U star, where U is unitary. It is orthogonal when x belongs to Sn, and D is a diagonal matrix consisting of real eigenvalues of x. So I start with my x, I get D, the set of all eigenvalues, real eigenvalues. Then I generate lambda x, which is the vector of eigenvalues of x written in the decreasing order. Then this lambda goes from V to Rn, is single valued and non-preserving, because the norm of x computed in this inner product space is the same as the norm of D, and the norm of D is simply the norm of lambda x. And the advantage of working with this lambda is that it is single valued and non-preserving. Now we come to some important results. In V, x dot y is less than or equal to lambda x dot lambda y. Notice that x dot y, x and y are matrices. X dot y is computed in V. It is the trace of x times y, while lambda x and lambda y are vectors in Rn, and that inner product is computed in Rn. This is the ordinary inner product. Now, this inequality is proved or was proved by Richter in 1958. Now, there is a reference due to Tin Yao Tam, and he refers to this inequality. He refers to this thing by quoting a paper of Fan, that he wrote in 1949. And I could not justify this out of this result of Fan. That's why I put a question mark there. But I have used this reference of tan so many times, I believe that what he is saying is right. And that is the reason why I say that this could have been given by Fan. And that is the reason for using Fan's name in the FTVN system. I may be wrong, but it is explicitly given in Richter's paper of 1958. This inequality is proved. In 1975, Theobald in England shows that x dot y is equal to lambda x dot lambda y if and only if there is a unitary matrix U such that x is U diagonal lambda x U star and y equals U diagonal lambda y U star. Notice that lambda x is a vector. So diagonal of lambda x is the diagonal matrix where you put lambda x on its diagonal. So Theobald characterizes the equality in this Richter's inequality. And it took almost about 15 years, 17 years to prove the to look at the equality case. I was told that this Richter's proof is analytical. Mirsky proves these results in an algebraic way. There is a later paper of Mirsky where he proves all these things in a very simple, elegant way. Okay, so these two results generalize Hardy-Littlewood-Polya result to matrices. Now we come to orbits. In V, remember V is nothing but either Sn or Hn. Matrix X belongs to the lambda orbit of Y if and only if lambda X equals lambda Y. Or equivalently, because of this spectral decomposition result, Y is nothing but Ux U star for some unitary matrix U. Thus, the lambda orbit of X is nothing but Ux U star where U is unitary. Aside, linear transformations of the form X going to Ux U star are the only invertible linear transformations on V that keep the Jordan product X circle Y invariant. So this is another way of introducing this transformations X going to Ux U star entirely in terms of the Jordan product. Okay. We claim that this triple V lambda is a FTVN system. I think there is a typo here. It should be V R N lambda. It is not V lambda. So there is a typo. The claim should read V R N lambda is a FTVN system. Let's see. In view of the time, I can skip the proof. The proof is given there. It's very simple. All one has to do is to use the Richter's result to get the inequality, and the equality can be seen just by looking at the spectral decomposition of C and defining an appropriate X. I'm going to skip this particular thing. Okay. So we know that V Rn lambda is a FTVN system. Now let us consider in particular the system Hn, Rn, and lambda. Now I have corrected this typo here. As observed above, X and Y commute in the system if and only if there is a unitary matrix U such that X is given as U diagonal lambda X U star and Y equals U diagonal lambda Y U star. Now in particular, commutativity in this system implies XY equals YX. That is our usual commutativity. However, the converse is not true. That X and Y be 2 by 2 diagonal matrices with diagonals 1, 0 and 0, 1. So as diagonal matrices, they commute. But when you go through this lambda X and lambda Y and check X dot Y, the equality of X dot Y and lambda X dot lambda Y, you will see that they are different. So even in the case of matrices, usual matrix multiplication or usual matrix commutativity is different from commutativity in the corresponding FTVN system. This becomes important later on. As we did in the case of Rn, I can describe this entire thing in a polynomial way. So this is our polynomial approach. For x in V, let P of x be simply the determinant of x. This is a real homogeneous polynomial on V. Now with E equals the identity matrix, the roots of the univariate polynomial T going to P of Te minus x, which is nothing but the determinant of Ti minus x. And this roots are all eigenvalues of x, and we know that they are real. With lambda x denoting the roots of this polynomial written in the decreasing order, one can define the inner product as done previously, that is that expression, and verify that x dot y is less than or equal to lambda x lambda y. This is one clever way of proving Richter's inequality, or rather Fan's inequality, via this polynomial, via this polynomial. And this is done in this paper of Boschke et al. Coming to majorization in V, remember once again that V is either Sn or Hn. If I take two matrices E and B, the classical definition is that A is majorized by B if lambda A is majorized by lambda B in Rn. Now we have the standard notation A majorized by B, and Ando in 1999 proves that A is majorized by B if and only if A is a convex combination of matrices of the form U, V, U star, where U is a unitary matrix. Using our language, A is majorized by B if and only if A is in the convex hull of the lambda orbit of B. So whatever we had in Rn is carried over to matrices. See the similarity here. Well, previously we dealt with spaces of real symmetric or complex Hermitian matrices. Now I can look at space of all n by n matrices. I'm going to be quick here. Let M sub n denote the space of all n by n complex matrices. This can be turned into a real inner product space under this inner product real part of the trace of x star y. And if S of x denotes the vector of singular values of x, which are the eigenvalues of square root of x star x, then I can use this S of x and write the singular value decomposition. Rather x in Mn gives rise to x equals u diagonal S of x times V, where u and v are unitary matrices. Now, von Neumann, way back in 1935, proves that in Mn, M sub n, x dot y is less than or equal to Sx dot Sy. Notice that the x dot y is computed in Mn and Sx dot Sy is computed in Rn. And you have the inequality. With equality, if and only if x and y are given in some specific form. X equals u diagonal S of x V and y equals u diagonal S of y times V for some unitary matrices u and v. Now, as before, we can use this result of von Neumann and verify that the triple M sub n or n S is an FTVN system. So, at this stage, we have seen the results of Fan, rather of Richter, Theobald on von Neumann, and all of them say that certain conditions hold. And this is the motivation for me to introduce the definition of FTVN system. Now, let me talk about hyperbolic polynomials. This is quite important, and this leads to lots and lots of interesting open problems. Hyperbolic polynomials were introduced by Gowda in 1959 in connection with partial differential equations. What is the definition? Let V be a finite dimensional real vector space. Assume that you have an object E in V, and let P be a real homogeneous polynomial on V. We say that P is hyperbolic with respect to E if P of E, notice that P is a polynomial. If I plug in E, what I get is a number. P of E is non-zero, and for every x in V, the roots of the univariate polynomial T going to P of T E minus x are all real. That's it. That is the definition of a hyperbolic polynomial with respect to one particular direction E. Now, once you know that the roots are real, for any x in V, that lambda x denote the vector of roots of this univariate polynomial with entries written in the decreasing order. So, depending on the degree of this polynomial P, this lambda x belongs to appropriate Rn. Now, Gowda shows that this set x such that lambda x bigger than or equal to 0. Notice that lambda x is a vector in some Rn with decreasing components. When I say that lambda x is bigger than or equal to 0, I'll be saying that every component of lambda x is greater than or equal to 0. Gowda shows that this is a convex cone. This is the so-called hyperbolicity cone corresponding to T. Optimization relative to this cone is called hyperbolic programming. What are special cases? If P is simply restricted to Rn, where P of x is the product of the entries of vector x, you get the non-negative orthen that leads to the standard linear programming. If V is Sn and P of x is the determinant of x, where a capital X is a symmetric, real symmetric matrix or Hermitian complex matrix, then lambda x is simply the vector of eigenvalues of that matrix written in the decreasing order. Then this hyperbolicity cone is nothing but the semi-definite cone, and the corresponding optimization leads to the semi-definite program. So this current thing in optimization deals with hyperbolic programming, whether linear programs on this hyperbolic cone can be solved in polynomial time or not. Now, examples of hyperbolic polynomials are, I'm going to make a list here. The first two have been described previously. The third one is interesting. On Rn, I take P of x equals x1 square minus x2 square dot 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 minus xn square. I take E to be 1, 0, 0, 0, 0. The last example may have been the reason for the use of the word hyperbolic in this analysis. Notice that if I look at P of x, it is generated by a matrix whose eigenvalues are 1, negative 1, negative 1, dot, dot, dot. And if I simply restrict this to 2, I get x1 square minus x2 square, and that gives a hyperbola. The corresponding hyperbolicity cone in the last example is this famous Lorentz cone or the second order cone or the ice cream cone. When P is complete, which means that lambda x equals 0 implies x equals 0, V becomes an inner product space under this inner product. This is what is covered in this paper of Bauschke et al. Written in 2001. It's a very influential paper. We say that P is isometric if certain condition holds, and this condition involves lambda of the sum C plus x equals lambda C plus lambda x. So this lambda becomes additive on this sum. Okay, it can be shown that when the hyperbolic polynomial P is complete and isometric, the triple V Rn lambda becomes a FTVN system. However, beyond the definition of complete and isometric properties, no characterization is known. I don't know of any literature dealing with completeness and isometry except this paper of Bauschke et al. not many examples are known. So one open problem is to look at characterization of complete isometric hyperbolic polynomials and construct examples. All right. So far, we have seen number of examples of FTVN systems, and the reason why we have used the names of Fan-Theobald-von Neumann, and this appearance of Fan may be misleading. It should have been replaced by Richter, but that is a debatable thing. So I'm going to just leave it as it is. There are other important examples of FTVN systems, namely Euclidean Jordan algebras, normal decomposition systems, and Eaton triples. I will mention these at the end of the talk. I may not have time to go over those, but the slides are there for anyone to read and understand. Okay. Next, I'm going to talk about commutativity in FTVN systems, and then talk about majorization and the doubly stochastic maps. Recall that in a FTVN system, two elements x and y commute if x dot y is the same as lambda x dot lambda y. Now we introduce a number of results and concepts related to this commutativity. In a FTVN system, the center consists of those elements in V that commute with every element of V. This is the concept of center that comes from ring theory or algebras. A non-zero element E in V is a unit element if the center is simply R times E, a set of all multiples of E. And FTVN system may not have any units. The center may be just the zero element. In the case of Sn or Hn, identity matrix is a unit element. That's it. Now, here is a very simple result. I mean, whenever I state a result that does not go with a name, it is described in one of my papers mentioned at the beginning. So here is a result. In a FTVN system, the following code. Lambda, the eigenvalue map, is positive, homogeneous, and Lipschitz. So this automatically gives continuity and all that. X and y commute if and only if lambda of x plus y equals lambda x plus lambda y. Now this is new even for matrices. Remember, commutativity in an FTVN system is much more than the ordinary commutativity. Commutativity in this FTVN system is related to lambda being additive on the sum. Lambda of x plus y equals lambda x plus lambda y. The center can be zero or non-zero. The center is a closed linear subspace of V, and lambda is linear on it. Now, one can ask, how does one prove these things? The deepest result I have used so far is a separation argument that one is familiar in a standard functional analysis course or matrix theory course. That's all I have used so far. There is a related decomposition result, factorization result. Take any FTVN system, but here I assume that V is a Hilbert space. Okay, because I need some separation theorem where I want the linear functional to be of a particular type. That is the reason for using a Hilbert space here. Take a FTVN system where V is a Hilbert space with C denoting the center. I can always decompose V as the direct sum of the center plus its orthogonal complement C per. And it turns out that CW lambda is an FTVN system whose center is all of C. So it has the full center. Any two elements in this thing commute. And C per comma W comma lambda is an FTVN system whose center is trivial, namely it is zero. So any FTVN system, as long as V is Hilbert space, it could be finite dimensional, can always be decomposed into two FTVN systems where one has the full center, another has the trivial center. This is a very interesting decomposition result. Our trivial example 2 has full center and M sub n, as described earlier, as trivial center. Next, I'm going to talk about spectral sets. In a FTVN system, a set is a spectral set if it is of the form E equals lambda inverse of Q for some Q contained in V. Now, so this spectral set is just a union of lambda orbits, nothing else. So whenever you have a set that can be described in terms of eigenvalues, that gives us a spectral set. Now, in the case of this FTVN system Rn lambda, a set is a spectral set if and only if it is permutation invariant. Permutation invariant sets are also called symmetric sets in the classical literature. Example, semi-definite cone. Semi-definite cone. Semi-definite cone is a spectral set in a set. The following sets, okay, 1 second please. Bye. Sorry about that. The following result shows that the property of being spectral is invariant under certain algebraic and topological operations. So this shows the importance of sets being spectral. Take an FTVN system, and if E is a spectral set, then the closure, the interior, the boundary are all spectral. And in the case of a finite dimensional space, convex hull of a spectral set is spectral. And if V is a Hilbert space, the closed convex hull of a spectral set is spectral, and the polar is also spectral. Now we come to linear optimization. This result essentially says that maximizing a linear function over a spectral set in V is the same as maximizing a related linear function over a set in W. Now this becomes important in semi-definite programming. Supposing you're maximizing a linear function over a set in Sn or in Hn, and the set is described by means of inequalities involving eigenvalues. You can transform that problem into a problem in Rn. And problem in Rn may be much simpler to solve than the problem over matrices. And that is the reason why this result becomes important. So what is the result? You take a FTVN system. If I fix a C in V and take a spectral set E, the functions f and f star are defined as follows. F of V is C dot V. Notice that it is a linear function on V. And f star W is lambda C dot W. It is also linear, but it is defined over W. Then the maximum of f over E is the same as the maximum of f star over lambda of E. So the problem over E is converted into a problem over lambda of E. And lambda of E is in W, and this second problem may be much easier to handle than the first one. And that is the relevance of this particular thing. And the proof is extremely simple, because in one of the defining conditions of this FTVN system, we use the third maximum property. That maximum property is over a lambda orbit, but the spectral sets are not too far from lambda orbits, because a spectral set is, after all, a union of lambda orbits. And for that reason, from that third condition in the FTVN system, this theorem can be proved. Commutation principles. I'm going to be quick here. I see that I'm already over the time. Let us consider the key defining condition of an FTVN system. Certain maximum equals certain value, lambda C dot lambda U. when the objective function c dot x attains its maximum on this lambda orbit, say at x bar, then we have c dot x bar equals lambda c dot lambda u, but lambda u is the same as lambda of x bar. So you see that c dot x bar equals lambda c dot lambda of x bar. This means that c and x bar commute in the FTVN system. So built into this condition, the third condition of the FTVN system is this commutativity condition. A similar statement can be made when this lambda orbit is replaced by a spectral set. So commutativity becomes an optimality condition for a linear maximization problem over a spectral set. There are a number of such commutation principles in the literature, especially for this matrix spaces Sn and Hn, and also for Euclidean journal algebras. And these have appeared recently in various journals, such as SAM Journal of Optimization, Math Programming, and things like that. Here is a very simple geometric computation principle. If E is a spectral set in an FTVN system, and if A is an object in E, then any outward normal to E commutes with this A. This is a very simple geometric commutation principle, and the definition of an outward normal to E at A is given. It is a vector D, such that D dot x minus A is less than or equal to 0 for all x in E. There is a very simple proof, nothing complicated at all. It is just like 5 lines. I'm going to skip that. If anybody wants to know the proof, we can always come back to this, and I can explain it. Okay. Here is an application to variational inequality problems. Given a function g, v to v, and e contained in v, the variational inequality problem vi, g comma e, is to find a vector a in e such that this variational inequality holds. G dot a comma x minus a is greater than or equal to 0 for all x in E. When E is a closed convex cone, this reduces to the famous complementarity problem. And as is well known, these problems appear in partial differential equations, optimization, game theory, economics, rigid body dynamics, etc., etc. One very simple result that comes out of the geometric commutation principle is that if E is a spectral set and A solves Vi of the variational inequality problem for the pair G comma E, then A and minus G of A commute in our FTVN system. So if you are solving a variational inequality problem that corresponds to a spectral set, this becomes useful. And it is useful in the semi-definite setting or even in Rn. Moving on quickly, one can define majorization in an FTVN system by saying that x is majorized by y if x belongs to the convex hull of the lambda orbit of y. Now notice that this requires only the knowledge of lambda orbits. However, when all the conditions of an FTVN system are in force, one could get meaningful examples and results. Here is the definition of a doubly stochastic map on an FTVN system. And you have a FTVN system V W lambda. A linear map D from V to V is doubly stochastic if dx is majorized by x for all x in V. We saw this type of a condition in the setting of Rn and Sn and so on. I'm just using that as my definition in this general FTVN setting. Here is an interesting result that mimics classical results. Suppose D is a doubly stochastic map with adjoint D star. Then for every convex spectral set K, D of K is contained in K. So if K in the setting of Rn is the non-negative octant, then D of Rn plus is contained in Rn plus. So that says something like D being a non-negative thing. And the second statement, if E is a unit element, then D of E is E. In the case of Rn, the unit element happens to be 1, 1, 1, 1, 1. Then D of E equals E simply says that the row sums are 1, and D star of E equals E refers to the columns and sums being 1. Okay, so you see the translations here. The third one simply says that if D is doubly stochastic and V is finite dimensional, then D star is also doubly stochastic. There is some blur about the equivalence of item A to D being doubly stochastic. I'm going to skip that, that is not relevant. Let me mention the following. The condition B of E equals E is usually referred to as the unital property, and D star of E equals E as the trace preserving property. These things are used heavily in the setting of quantum computation, quantum analysis, and all that. Particularly, there is this beautiful theory of completely positive maps of Choi and other people. So these things become relevant there. In certain settings, such as SN, HN, Euclidean Jordan algebras, and all that, apart from D of E equals E and D star of E equals E, it is enough to show that it is enough to require D to keep only one spectral convex set, such as the non-negative orthant or the semi-definite cone invariant. However, whether this is true in the case of hyperbolic polynomials and hyperbolicity cone is an open problem. This is kind of a very interesting problem. It could be a research problem, it could be a PhD problem, I do not know. This is completely open. Here are some slides regarding Euclidean Jordan algebras. Definition is given and examples are given. There is a characterization result. I'm going to skip all these things. Definition of normal decomposition system is given. There is also this definition of Eaton triples given. So these are part of the appendix. Jordan algebras, normal decomposition systems, and Eaton triples. I don't have time to cover this. I think I've already taken more time. So I'm going to stop here and take some questions. So thank you very much for coming and listening to my talk. I appreciate that.
Yeah. Thank you very much, Professor, for the interesting talk. Yeah. Audience, if you have any question, we can ask them.
Yeah, I wanted to know, are you dealing throughout with finite dimensional Hilbert spaces? Or
No, not at all. In fact, in the third article that is forthcoming, we have given an example of an infinite dimensional FTVN system, and that has to deal with a sequence space. You know that in measure theory there is this concept of rearrangement functions and all that.
Yeah.
So we have used that one and some results of RD, Littlewood, Polya, and all that to create this particular infinite dimensional example of FTVN system, and that is not trivial at all.
I can imagine.
Yeah.
Okay, thank you.
Yeah. Are there other questions? Professor, I have a question.
Are you going to make your slides available, Professor Gowda?
Say it again.
Are you going to make your slides available?
Yeah. I'm going to send it to Rajesh.
Okay.
So he is going to post all the slides as well as I believe the YouTube presentation, and that is new for me. So I don't know how it's going to turn out. So I'm going to send all the slides to him, and he can post it. Yeah, and that I think that is the normal procedure.
Yes, sir. So,
Thank you.
I will circulate the slides and video link with all the participants.
Yes.
Yes. Yes.
Yeah, I'm going to forward the slides to him.
So when you consider this set of all symmetric matrices,
Yes.
so you have taken the polynomial to be the determinant polynomial, and you have visualized that as a like the FTVN
Correct.
system. So suppose if you replace the determinant polynomial with some other polynomial, let's say by permanent, something like that.
That's a very good question. As I said, apart from these standard examples, not many examples are known. Although now there are number of papers written on this hyperbolic polynomials. There are some people in France and Netherlands. There is an Indian person. His first name is Raman. I forgot his last name. Now they are doing very difficult. They are coming up with some very interesting and difficult results on hyperbolic polynomials. But I have not seen simple hyperbolic polynomials which are complete and isometric. There is this paper of Bauschke, and that's it. Nothing else is known. So you can take a polynomial x1, x2, xn. Then out of that, you can create other symmetric polynomial. For example, if I take in R2, x1 times x2, then out of that, I can create x1 plus x2. If by differentiating, I can create x1 plus x2. That also turns out to be hyperbolic. So you start with a hyperbolic polynomial, differentiate that appropriately, you generate more hyperbolic polynomials. But whether they are complete and or isometric is an open thing.
Okay.
That is why I said I've not seen too many examples. That itself is a problem. And this problem I mentioned about describing doubly stochasticity over the hyperbolicity cone is another interesting problem.
Okay, thank you, Professor.
Yeah, Professor Vidyasagar, are you in Hyderabad?
Yeah, I'm in Hyderabad. Yes.
Okay, I appreciate just sending me your email address so that
Sure,
I can
I'll do that.
correspond with you.
Yeah, I'll mail you. I'll send you an email which has my details. To do that.
Okay, thank you very much. Thank you.
Are there other questions?
Hello, sir. It's Gokul. I have a simple question. Like
Yes, yeah. Go ahead, Gokul. Yes.
yeah. So the hyperbolicity cone you have talked about. So as
Yes.
we change the corresponding polynomial, so the cones are coming as semi-definite cone, Lorentz cone, kind of
Correct.
things are coming. So
Correct.
as we see in those examples, all those cones are they are all self-dual and kind of symmetry. So do we expect in general that hyperbolicity cones are self-dual from nature?
No, not at all. Not at all.
Is there any studies on hyperbolicity?
No, okay.
cones?
See, these so-called symmetric cones that you mentioned, they are both homogeneous cones as well as self-dual cones. Homogeneity means that if you take any 2 points in the interior, then there is an automorphism which maps one to the other one. Okay, so the symmetric cones that arise in Euclidean Jordan algebras are extremely special.
Yes.
They are homogeneous as well as self-dual. So if you drop self-duality, you get homogeneous cones, and there is a beautiful theory of invert dealing with homogeneous cones. And it is known that homogeneous cones are also hyperbolicity cones. This was one of the results put by my colleague Osman Buehler way back in the 90s. Yeah, so they're very extremely broad.
Okay.
So if you can do something even elementary in the context of hyperbolic polynomials, you could have made a big name.
Okay. So is it good idea to think about bilinearity, rank, such things on these cones?
You can think of
Is it
them,
possible?
but they are not easy. Don't, I mean, if you're looking for a research problem at the PhD level, these are highly complicated.
Oh.
I would not suggest that.
Okay. Thank you.
Okay, they're like, it's a different league.
Okay.
I mean, there are top people in Berkeley and other places are working on these.
Okay.
You know, I mean, my intention is to connect these things so that you see where all these things fit.
Yeah. Let's see.
You know, but there is still some scope for working on majorization, double stochasticity, and things like that. Those things can be done. Yes.
Thank you, sir. Thank you for it.
You're welcome. Yeah.
Okay. Are there other questions? Yes, sir. If not, let us thank Professor Gowda for his interesting talk.
Thank you very much.
Thank you.
Appreciate that. Thank you.